Okay, welcome back. We are doing lessons 76 and 77 today. Yes, we're going to do two lessons. They're both fun lessons. Lesson 76 is symmetry. Symmetry is a property illustrated when the image of a transformation of a figure coincides with the pre-image. Now that doesn't really help us at all, but we'll explore it more. There are several different kinds of symmetry. One is line symmetry. A figure has line symmetry if a figure can be reflected across a line so that the image coincides with the pre-image. The line that divides the figure into two congruent reflected halves is a line of symmetry. So the figure at right is a vertical line of symmetry, has a vertical line of symmetry. I think we maybe sort of understand it, but here's a vase, a lovely vase that was sitting on that windowsill over there. And this vase has symmetry. I don't know if you can see the detail or the designs, but I mean, back here, just the overall shape, it's symmetrical. We could draw it up here, and we draw a line like this. And in fact, in drawing programs, I do use it sometimes. I'll draw one half of something and then just reflect it across the line. So it's really like you draw half of a figure and do a reflection of that figure. So this figure would look something like this. It comes out and then goes down and goes out like that. Reflect that across and you get the rest of the vase. But actually, it has more than that because there's designs in it. And you can see the designs. If I hold it just perpendicular like so, then there's also a line of symmetry right here, and including the designs are half and half. And also if I rotate it this way to right there, I guess, get my marker out of the way. Right there you would see it again. You can imagine a line going right down the middle of that, and then this half is perfectly equal to this half if I hold it just right. So this is three-dimensional object. You can have symmetry. Three-dimensional objects can have symmetry. Two-dimensional objects can have symmetry. Obviously, there's more drawings that have symmetry. This is all line symmetry. You know, a heart, a perfectly drawn heart will be symmetrical. This one is not perfect and it looks bad. The reason is this is much higher than the other. If I would, so the best way to draw a heart, and y'all probably have done this in school, is you take a piece of paper and fold it in half, and then this is the folded half sheet right here. This is the fold on this side. This is a big piece of paper. Let's make that a little smaller. Take a piece of paper, fold it in half. Here's the fold right here. And then cut out a shape like that and unfold it, and it will look a lot better. It will look much more like a heart. The reason is because you cut both lines at the same time, so they'll be exactly congruent or symmetric. Example 1, letter B. Identify whether each figure has a line of symmetry. The quadrilateral is not symmetric across any line anywhere. That's an ugly figure. And while we're talking about line symmetry, people are symmetric, and people's faces, we'll stay with people's faces, but people's faces are symmetric. Their hands are too, and whatever, but some people's aren't. Some people have. My dad has a missing finger like this, so he's not symmetrical. If he holds his hands out, this one is missing and this one's not. But if you look at your face, you've got two eyes, you've got one nose, but two nose, nostrils, a mouth in the middle, two ears. And there's people that say that the more symmetric your face is, the more beautiful you are. Now, we're not going to talk about beauty, but there is something pleasing about symmetry. And an interesting thing is to take a mirror like this. I can kind of make the camera look funny by flashing this light. Take a mirror and look into a mirror. In this case, I'm looking into my iPad screen. But do this at home sometime, and it's kind of hard. But if you I don't know if you can see it or not, but I'm looking in here. But I need to look out here while I'm doing it. And then put this mirror just right. You can make a face, kind of like, and I can make myself have a really big nose or a really small nose. But you try to orient it to where you're looking at this half and then a reflected half, and it looks different than what you look like this way. In fact, most people's faces are not perfectly symmetrical. If you study your face in the mirror, me anyway, my mouth is a little crooked, and maybe one ear is a little taller than the other, whatever. And that's the reason why, not so much nowadays, everyone is used to looking at yourself in your camera screen or looking at pictures of yourself. But I remember younger days growing up, and I started to see photographs of myself, and I looked weird. I thought I looked funny. The reason I looked funny is because I was used to seeing my face in a mirror, and looking at your face in a mirror is different than looking at yourself as somebody else sees you, which is the way a photograph would do it. And the reason is because it's switched. A mirror reflects like this, where people looking at you straight on in real life, they get the opposite side of it. And it's the case for, let's say, somebody you are familiar with, in my case, my wife. I know how my wife looks, her face, and I see her, if I look in the mirror, her face looks different. If I see her through the mirror, so I'm in the bathroom, I'm talking to her through the mirror and looking at her, talking to her, her face looks different if I look at it through the mirror than what it is when I look at it in real life. And it's the same, it's the symmetric thing. It's because our faces are not perfectly symmetrical, then being used to your face through a mirror or being used to your face in real life or through a photograph is two different versions. And that is why, for me, seeing my face or seeing myself first in a photograph is like, oh, that looks funny, I look funny. And the reason is because it was looking at my face the opposite way, which is proof that my face is not perfectly symmetrical. And if you could do this very well, you do it this way on this half and get it just right, and it would look like one thing. And if you do it on this half, your face would actually, I can't get it lined up, but your face would actually look a little bit different with the reflecting half. It probably would be better to do it, and I'd like to see somebody's picture if they do it. Take a picture of your face and put it into a computer program and cut off half and flip the half. I'm sure there's programs that do that. Probably even an app that does that, I don't know. But you do one half and your face will look slightly different than if you base it off of the second half. All right, that is all line symmetry. There's one line through the middle. There's other types of symmetry. Rotational symmetry is a type of symmetry which describes a figure that can be rotated out about a point by an angle less than 360 so that the image coincides with the pre-image. Now that's a big mouthful, but that kind of logo looking thing on the top of page 501 is an example. And the smallest angle through which a figure can be rotated in order to coincide with itself is the angle of rotational symmetry. So let's just say this mirror right here. Well, that's not going to work because you see, what do you see? Oh, you see my camera mount. That is a crate. Let's see if I back up. I need a bigger mirror. There's a chair, or there's a table, or there's a table, and then there's a folding chair, and then there's a black crate, and then there's an iPad hanging there, and that's the camera. But I have a feeling if I do this, we'll get close to infinity here. If I bring this up, can you see it? Yes, you can. I like that. I really like that. You bring it up, bring it up, bring it up. There's a mirror. If I line it up, I need lighting to show. There's a mirror, then there's a picture, then there's a mirror, then there's a picture, then there's a mirror, then there's a picture. I wish I had a flashlight. I never saw that before. I like it. Oh, I got to get over here to the, yeah, it messes up. The closer I get, it messes up because the camera screen is not exactly in the middle of the display screen. So the closer I get, the worse it gets, but I like it. I really like it. I'm getting lost in infinity there. I get too close. Whoa, that got really crazy. I don't know if you all can see this, but that is pretty cool. Anyway, back to rotational symmetry. This figure can be rotated. This is really not working. That is distracting. All right, let's do this. Here's a blank paper. And here it is. And if I rotate it in the middle, if I rotate it 90 degrees, the new image does not coincide with the pre-image because it's now oriented like this. But I can rotate it 180 degrees, and then I get exactly what I started with. So this rectangle has a angle of rotational symmetry, and that angle is 180 degree rotational symmetry. It coincides with itself after 180 degrees. Now, obviously, every figure coincides with itself after 360 degrees. If you go the whole way around, then it doesn't matter what shape it is, it will coincide with itself. This image, this trusty Germex container, ignore the writing and everything, just go with the shape and this spout and everything. If I turn it 180 degrees, I hope it doesn't leak, but it does not coincide with itself. If I turn it 360, it does. So this bottle, this shape, this profile does not have rotational symmetry. And I'm looking at just the profile of the bottle. In fact, it doesn't even have line symmetry the way I have it now because of the spout. If I turn the spout exactly to the camera or behind, then it would have line symmetry right through the middle. This goes in and this goes in right here. Both of them go up. It goes up, so it's line symmetry if you do it that way. Rotational symmetry, angle of rotation. Think about a perfectly drawn hexagon, which this is not. But we're back to rotational symmetry. I can take this hexagon and I begin to rotate it. And when is the first notch that it would coincide with the new one? I mean, with the original one. When I made 2 copies of it, and they're clear, so I can see through it. I should have done this, but well, I was feeling that taking this line right here and moving it to here, that is like this, moving to here, it would stop and it would fit perfectly, and it will. And that angle is related to this. 1, 2, 3, 4, 5, 6. There are 6 notches as I rotate this. Each 60 degrees, it would coincide with itself. So it's 360 divided by 1, 2, 3, 4, 5, 6. So every 60 degrees, it would click and fit exactly right, and you couldn't tell where I'm at in rotation. So order angle of rotational symmetry. A regular hexagon has an angle of 60-degree rotational symmetry. Oh, that's just what it said there in the book. It also has line symmetry. You can go this way, you can go this way, even with these things drawn in here. It has 2 lines of symmetry this way. It would have more actually. You can go this way, you can reflect it across an angle this way. So it's got all kinds of line symmetry. It also has rotational symmetry. Now, example 2 says you can create symmetrical figures using transformations. And so like the example, I want to go back to rotational symmetry with this. This is a logo that is on my computer. Thing is distracting back there. This is a logo that's on my computer. It stands for QuickBooks QB. QuickBooks, it's an accounting software program. This is the logo, and does this logo have symmetry? That's a question, and the answer is yes. But if I ask what type of symmetry does it have, then you shouldn't say line symmetry necessarily, because if I put a line like this and reflect it across, this is a P, this one's sticking down, and if I reflect it across it, it's sticking down here, it's not sticking up. But it does have rotational symmetry, and you should be able to see that by looking at it. And also the angle of rotational symmetry is 180 degrees, so I take this and rotate it like that, and I get back to where I started, which is a Q and a B. And I'm actually 180 degrees from where I started, so I'll do it again, go back to the original. This hand is on top, go here, so to prove it there, I have to go all the way around to get back to the original. Now, how could you decide where the center of this is? Well, it's the center of the circle, yes, but another way you could do it is if you would draw lines. If I draw a line from, say, this inside corner here, or let's go with this corner out here, up to this corner, draw a line, and then I draw a line from that corner to that corner where they intersect, and it would be right in the middle there. And I did it crudely with that one, but that's how you could decide where the rotation is. And you can't see through them, otherwise I could prove that doing one and it would go around and be perfectly symmetric or coincides with the other one. I kind of like this deal. If I put it like this and spin it, it just makes a nice looking shape. But this logo, since it's based on a circle, and that was intentional the way they designed it, but QuickBooks, that was the name of this company or the name of this software before they ever came up with this logo. But somebody decided somewhere that a Q and a B are somewhat symmetric. And if you draw them like this, then they're not QuickBooks, they're not. But you can obviously modify it a bit to get what you want, and then they are. And you do it here, and you add and then a circle around there. If they would have done some other logo, it had to have been a regular hexagon or something, but this is just nice about it, and also mimics this. I kind of like design, but somebody sat there and probably spent hours designing this logo, and they did it intentionally. They knew that it had rotational symmetry. I'm sure they did. But 180 degree rotational symmetry. I don't know, I like that. I'm going to design a logo that spins. So angle of rotational symmetry is, back to that hexagon, was what angle? Order of rotational symmetry. We're on the middle of page 501. Order is the number of times that a figure coincides with itself as it rotates. So it's related to the angle. So back to this hexagon. Well, that one looks a lot worse than the other one did. We said it has, if this is a regular hexagon, it has an angle rotational symmetry of 60 degrees. Every 60 degrees, it clicks back with itself, which means if you take 360 divided by 6, divided by 60 degrees equals 6. 6 times, which makes sense. It has 6 faces, so every time, and that's including back as it gets around to the other side. So angle is, if a figure has rotational symmetry, the way you know is if it coincides with itself other than back around, which is pretty obvious. Every figure will coincide with itself once you get all the way back around. But if it does it before that, then it has rotational symmetry, and then you decide what is the angle of rotational symmetry and what is the order of rotational symmetry, and those two are related. Angle is 60, order of a hexagon is the angle is 60 of a hexagon, and the order of the hexagon is 6. This thing coincides with itself 6 times as it goes around and gets back to 0. What about a square? Does it have rotational symmetry? Yes, it does. What is the angle of rotational symmetry? 90 degrees. You take it here and go 90 degrees, which means what is the order? The order is 360 divided by 90, so 4 times, and you can see that 4 times. Any regular hexagon, turn the page. We'll come back one, but right now go to 502, page 502. It's example 4. And it says tiles often have many lines of symmetry so that they can fit together in patterns. If you're a tiling person, or you see tile, or you have tile in your house somewhere, they're often regular polygons, and they have lots of lines of symmetry. So how many lines of symmetry does a regular polygon with up to 10 sides have? It's pretty obvious to me. Here's a triangle. What is the well, this is lines of symmetry, but it also is the same question. What is the order? The order is 3 for a triangle, 4 for a square, 6 for a hexagon, 5 for a pentagon, and so on. So how many lines of symmetry does a 15-sided tile have? It would have 15 lines of symmetry. It would also have an order of 15, which is 360 divided by 15 to get your angle. I don't know what a 15, whatever. But it would coincide 15 times as it goes around, and the angle would be 360 divided by 15. It's smaller than that probably. But angle of rotational symmetry and order of rotational symmetry. Let's go back now to the bottom page 501. Finding orders of rotational symmetry, just to reinforce this. A, does this example 3A, that's a big capital letter N, does that have rotational symmetry? Does a capital letter N have rotational symmetry? And the way to prove it would be to cut it out and actually do it, but you should be able to do it in your head and look and see that yes, it does. The bottom N, this bottom leg here, if you rotate it 180 degrees, it will be right there. And this one that was up is now pointing down, so yes, it does. And if so, give the angle of rotational symmetry and the order. The angle of rotational symmetry of a capital letter N, the angle is 180, which means the order is 2. B, 3B is a square within a square. It's a diamond within a square. Does that have rotational symmetry? I feel that it does. And what is the angle? If you imagine rotating that, rotate it 90 degrees, and it would lock into itself again. So the angle is 90, which means the order is 4. And then C, does that have rotational symmetry? You look at it and you could say, well, yeah, it does. Right in the middle, you rotate it, but it does not. Since that line goes like this, and this one mimics it, then if you flip it 180 degrees, these will now be up here like this, and so they don't coincide with each other. It has line symmetry right here, like this against this, but we're not asking for line, we're asking for rotational symmetry. There's more that could be discussed, but the symmetry in this lesson is line symmetry and rotational symmetry. And rotational symmetry is the one that has the most about it. The rotational symmetry, you will need to know the angle of rotational symmetry. Does that make sense to you? And how that the order of rotational symmetry. The order of rotational symmetry is simply how many times does it rotate onto itself, or does it coincide with itself? And order is related to angle. All right. That is lesson 76. We're going to go lesson 77 quickly. Finding surface areas and volumes of cones. What is a cone? A cone is a three-dimensional figure with a circular base and a curved lateral surface that connects to the base to the point called the vertex. Well, again, they use big words. I would like to say that the definition of a cone is a combination of figures. First of all, you have a circle on the bottom. A cone has a circle on the bottom, and then it has a point above the circle. Here's a circle, and there's a point above the circle. And then the cone consists of all points that connect this point up here to the circle, to the outside of the circle. And so you get something that looks like this, an upside down funnel. I just made this just now out of a piece of graph paper. I don't know if you can see it or not. Sort of you can. Looks kind of white. There are the graph lines, and I get around to the seam, and it looks funny. But if you go like this, it looks nice. A cone. So this doesn't have a bottom, but the shape is in a circle right here, and then there's a point up here, and all the surface connected to that. That's a cone. The circular face of a cone is called the base, which really makes sense because you could not talk about a cone like that. It doesn't work. This cannot be the base unless you have a top, like a spinning top, I mean. So this is the base. The circle is the base. The vertex is the point that's opposite the circle. The altitude, just like the triangle and whatever, is the perpendicular segment up here. It's not this. This is called the slant height. This distance is called the slant height. The up and down, straight up and down, is the altitude. If the altitude of a cone has an endpoint in the center of the base, then it is a right cone. In other words, if this point is centered above the circle, straight up from the center of the circle, then it is a right cone. If it's tilted, which it can be done, I can't make this one tilt, but if you have a kind of slanted cone, then it's an oblique cone. It looks like oblique, but we talked about that before, I think, as well. Oblique cone. In an oblique cone, the altitude does not intersect the center of the base. It would, a cross view would look like this, something like that. It'd be tilted, so you drop an altitude, which is the perpendicular, has to be the perpendicular, and it's nowhere near the center of the circle, which is here. The slant height is this distance, and the radius of a cone is the radius of the base. So from the center out to here, the radius of a cone is the radius of the base. All right, formulas, of course. Lateral surface area of a cone. So this is simply this outside here, not the bottom of the base, but this outside here. The lateral surface area, they give it with a big L. It's given by the formula where R is the radius and little l is the slant height. So symbols and names, but big L means lateral surface area, little l, lowercase l means the slant height. So the formula is pi times radius times slant height. Now I would love to do work on that and try to connect the dots as to why that is. Pi because there's a circle involved, and radius because there's a circle involved, but then times this. That's the lateral surface area. In other words, if I would unfold this thing, and then I'd have that pattern that we had looked at earlier, it would look something like this, depends how big it is, but that surface area, all this area. And we could find the surface area by doing our segment of a circle, remember that? Like if I know this degree is what this is, or we do a better one, it could look like this. We know what this angle is, so we can take that amount out of the circle, and we know the radius. We can find it that way, but if you put it together into a cone like this, then you can use the formula of pi times radius times slant height. You'll just have to memorize that. And then the surface area, the total surface area, of course, is the lateral surface area plus the area of the base. And we know how to find the area of the circle. Pi times radius squared, find that. Take that area and add it to the lateral area to get the total surface area. Now, one more is volume. What's the volume of this? And it's interesting to me that it's the same formula as a pyramid. It's finding the area of the base. If you turn the page, it'll be there. 508. It's finding the area of the base, taking it times the height times 1/3. So there's kind of a progression for square things, like squares. Of course a square is a square thing. Square things like squares, or rectangles. You have area of the base times the height, or the area is equal to the base times the height. That's how you find this area. For a triangle, it's area of the base times the height times 1/2, because we could chop it up and do two of them, that would be related to that. Or the other way to do it is look like this and say, here's my area of the base, and here's the height, and then go midpoint and make this be a triangle. Now I'm talking about just this area now, it becomes 1/2 because these two, you could fold them in or it would be like that. So anyway, area of a triangle 1/2, base times height. Area of a rectangle is base times height. And then a three-dimensional pyramid or this is 1/3 of base times height, but the base is the area of the base, and it's three-dimensional, we know that. But volume of a cone is 1/3 of the base times the height. So when you're asked to look at a cone and you're asked to get either the volume or the lateral surface area, you need to decide which is which, because the volume has to do with the height, which is the perpendicular, and the lateral surface area has to do with the slant height, which is not perpendicular. So make sure you use the right thing. Two different things, you get two different results. This is slant height, and this distance is altitude, which is what you use for the volume. That is the end of the lesson. Homework. Yes, homework. You have 7 days to do it, so you should not be groaning too much. I know it's Easter vacation, you're going to do whatever all else you're going to do, but it's okay, you still have homework. Homework for lesson 76 is 1, 2, 5, 9, 17, 21, 24, 29, and 30. Lesson 77 is 1, 2, 7, 11, 13, 14, 18, 22, 25, and 27. It's a good thing I stopped there because I ran out of whiteboard. Homework for lesson 76 and 77. Please have that done by Wednesday morning. Thank you.